Good afternoon, ladies and gentlemen. It's my pleasure to be here today and be able to present to you two of the major developments that we have been doing at Allnex that we really believe that can be a big support in the inkjet ink market. And so, as you see in the title, this presentation will deal with two major topics. One topic will be about the use of a LED booster in UV LED curing systems. And then a second topic, which I will start off with immediately, is the use of Waterborne UV for inkjet inks. Why would we be interested to use UV and Waterborne UV in inkjet? Well, you could have a look at what is on the market today, and you can basically put it into two major columns, the conventional systems and the UV curing systems. If you look at the conventional systems, the content it's of course you have often a polymer, you have of course the pigments, additives, and you need solvent to bring down the viscosity to a jetting viscosity. The solvent can also be water. This technology has some advantages, of course. If you look at the fact that it's an older chemistry, it's a very mature chemistry, so it is easily implemented, it is easily formulated, or more easily formulated. It also has known characteristics in terms of adhesion to different substrates, sometimes because of the use of the solvents. And also the initial investment for a printing press is lower than if you would have the same press with a UV installation. Every advantage has its disadvantage. If you talk about disadvantages with the conventional systems, you can state, compared to UV, that they have a lower curing speed. Generally speaking, they also have a lower resolution, a lower color density than UV systems, because you cannot pin the ink after depositing it. Also, the UV resin has much more links, so the mechanical and chemical and hydrolytical properties might be not at the same level as for a UV. And in case that you need a solvent to bring down the viscosity, you can also imagine that you already generate VOCs upon printing. If we take a look at the UV side of the table, we also need acrylated resins to cure. The pigments and additives are, of course, also needed. And instead of using a solvent to bring down the viscosity, we use monomers. And to light the fire, you also need the photoinitiator package included into your ink system. So here you have the very rapid curing, you have the improved quality. Generally speaking, you have a low VOC because everything is bound into the network after cure. And you get the properties of your ink. On the downside, you can state that if you have to print really opaque inks, the light has to get through the ink, and you need to be sure that you can cure it. So that's sometimes an issue. Also, because you use a lot of monomers to bring down the viscosity, there is a chance that they are not bound into the network and can migrate afterwards. So that together with photoinitiator fragments, that might be a big risk for low migration inks. And a general perception of a UV ink is that it smells bad. So that's what is on the market today. So why not try to combine the best of both worlds? That was the general concept that we worked upon to install this technology for inkjet inks. So by using a waterborne UV system, you get rid of the monomers because you again use a solvent, which is in this case water. Because it's a dispersion, also the smell of the ink is much lower. So we think that this is a key advantage for a printing ink. We already did some work on this in the past, and so we have already 3 commercial grades available, which you see on the slide, and they all have their key characteristics. So all of them have their advantages and disadvantages. All of them, which is nice to mention, is that they are all label-free. 2 of them also do not contain bisphenol A, which is ups and downs, a big issue in the printing inks. None of them are tech-free after physical drying, so evaporating the water will give you a techy surface. The third prototype, the third grade, sorry, the 2803 is slightly tacky. It's touch dry, but it's not completely tack-free. All of them are resoluble. This is, for us, a key advantage of this technology over waterborne conventional inks. Since they are resoluble in ink, resoluble in water, they will have less tendency to clog the printheads. In terms of migration, you see the orange dot. This we put because they are not intended to use for low migration, but there is a possibility upon good formulation that they, if you do the test afterwards and the low migration test, that they would be okay. Reactivity, we also put an orange dot, meaning if you compare it to traditional UV, they are a bit slower in reactivity. There are much bigger molecules. For a molecule to react, of course, you have to have the collision, so you can imagine that the kinetics are a bit slower than traditional UV. And they all are very flexible polymers, so you can imagine that in terms of adhesion, they have some good properties. But what was really bothering us is that we did not have anything here in the migration, low migration area for UV PUDs and inkjet. So we decided to do some additional developments and develop new products that fit, have this green dot for low migration. For this, we followed a specific strategy, which is aligned here in 4 different titles. First is we eliminate all the chemicals of concern. So we don't use tin catalysts, we don't use bisphenol A anymore, we don't use solvents, so just to be sure that afterwards you can't find them back. Also, we maximize the amount of product which has a higher molecular weight than 500, and everything that is below 500, we make sure that it contains at least 6 acrylic double bonds. So the chances that they are incorporated in the network afterwards are optimized. A third point is that we control the composition, meaning that we use stabilizers that are food grade, and also in production terms we apply GMP to be sure that you have the cleanest possible UV PUD on the market. And afterwards, we also do the analytical work. We also do the analytical test to find out if they are really living up to the expectations of low migration. On the right, you see the pie chart of one of these prototypes, the IRR 929. And you see, okay, there is 65% water, so 35% solid content. And if you make the calculation, more than 99.5% of it has a molecular weight higher than 500 Daltons. And in the same time, also a functionality of above 6. This leads to this table. This is the same table as you saw before, but with the new development products. They have their specifications. One of the 2 is tack-free after physical drying. That might be an advantage. The other one is tacky. In terms of reactivity, you see here the 929 is a green dot. In later experiments that I show you the results of, you will see why this is a green dot. Because of the use of the chemistry, we cannot avoid having a label on the MSDS. But it's only a danger label, which when you use an acrylate, you're almost obliged to put on this label. And of course, you can imagine, here it's mentioned that 929 and 953 could be mixed and matched to get the desired properties, but you could do this with the whole family, depending on what is the desired application. This slide sums up a bit what we understood from our customers, what are the main characteristics that we need to adhere to be able to deliver a UV PUD that could work for an inkjet ink. So we have a specific look at the ink stability, we have a specific look at the filterability of the UV PUD. We make sure that, or we try to make sure that it's jettable. We have a look at the resolubility. Of course, we don't want to miss out on all the advantages of a UV ink, so we have a look at the reactivity. In addition to that, we also look at the adhesion to different substrates, because we know that the inkjet printers want to print on a wide array of different substrates. And then last, we also have a look, of course, at the chemical and mechanical properties of the cured ink. We are not formulators. We only deliver resins to our formulators that make a UV ink out of it. So if we wanted to do the testing, we needed a formulation. None of the formulators are happy to give away their formulation because that's really their trade. So we worked together with Chemie, and they did a nice study where they came up with a starting point formulation for such a UV PUD based inkjet ink. This is the base of all the study that came afterwards, which I will present the results. So the first technical requirement that we wanted to discuss is the ink stability. So we made different kind of inks, so the different color inks. And then we have a look, we put it in the oven at 50 degrees for a couple of weeks. And after a couple of weeks, we take it out, we measure the viscosity, and also have a look whether there is sedimentation or not. So if you don't see a second bar or third bar, this means that there was sedimentation. And because there's sedimentation, we did not measure the viscosity because it would not be representative for the real ink. But it's nice to show that in this case, the new development, I took the example here for the 929, that we were able to manage to get to 6 weeks without a lot of difference in viscosity. For the magenta ink, we got into trouble. We had some phase separation, but probably you guys know better how to deal with this than we do. But so just to show you, not all the prototypes were immediately a success. You see the black ink here on the side, which was completely phase separated, one solid block in the bottom. So yeah, we took this up and we tried to come up with a solution, and I think that this is one example of 4 color inks where we managed to, this is a picture after 12 weeks, so with complete stability of the ink. Sorry. Second technical requirement, water resolubility. In fact, it's not resolubility, it's redispersibility, because it's the dispersion that goes back. We have we can divide it into 2 families, the 929 and the others. The 929 has a very high molecular weight polymer, so you see that the redispersibility is not perfect immediately. It takes a bit more time. So you see some peels, and upon time, these peels disappear and get back into the dispersion. So, but it takes a bit more time, and maybe if you put in a bit more energy, because the water is at room temperature. So this is after 1 minute. You see that you get the peels. For the other ones, you see a complete redispersion of the ink when put in the water. Talking about ink reactivity, I already mentioned the green dot for the 929. In our lab experiments, okay, we made a drawdown with a nickel proofer, so we have a 4 micron thick layer to cure. And we were able to cure this IRR 929 at line speeds of 100 or above. So the formulations are not optimized, so maybe could even get better. But you see that compared to all the other UV PUDs, this one is really the king of reactivity. Last but not least, what I wanted to show you about this topic is that we also tried it on different substrates. So on paper, generally there is no problem. But I wanted to show you some results on difficult plastics, what we perceive as difficult plastics to get adhesion on. So in any case, we performed corona pre-treatment of the substrate to be sure that you get a good wetting, because we do not have the knowledge of all the additives that you could use to get to the perfect wetting of your substrate. And as you see, all of them have a different pattern, meaning that the darker the dot, the better the adhesion was. And you see that although the reactivity, generally speaking in UV inks, the higher the reactivity, the more difficult it becomes to get a good adhesion. The 929 is quite decent as well in adhesion to an array of different substrates. Coming to the second topic. is a second big project that we have been working on a lot at Allnex. Using UV LED. UV LED in inkjet printers, I've seen at Drupa, is almost all of the time you see an inkjet printer with UV LED. But we know there are some difficulties that remain when you want to use a UV LED. So if you buy a UV LED of a 395 nanometer, you know that you will have an equipment that emits around the wavelength of 395. If you buy a 405, it will emit around 405, etc., etc. Compared to a mercury bulb, you don't have an infrared component. And this is why a UV LED will have less heat on the substrate than with a traditional mercury bulb. As you see, you also don't have a UVC area. And because of this narrow emission band, of course, if you take into consideration the photoinitiators that are currently on the market, you're really limited. The toolbox is very, very slim. In fact, only the acylphosphine type photoinitiators and some others like ITX, DETX 369 absorb in this area. If they don't absorb in this area, well, then the light doesn't hit the photoinitiator, and nothing will happen. So you're a bit restricted to this if you want to use UV LED. Because these photoinitiators are all designed for getting better true cure and not really surface cure, this does not help. Because you have oxygen inhibition. If you have a thin layer of coating, and you have an oxygen in the environment around the coating, it will diffuse through the coating. You will have the highest concentration of oxygen on the surface. And that is a bit the problem. With the UVA LED, the UVA light will penetrate the coating very deep, no problem, but it does not attack the surface. And you can imagine if you put in a lot of pigment, which we want to get the nice colors, you will have a competition of absorption of the light by the pigment and by the photoinitiator. The yellow clouds are drawn there on purpose because we know that for the yellow pigments the competition is the heaviest competition with the photoinitiators. So talking a bit about the oxygen inhibition and how to keep it from interfering. There are some different technologies available today that can already help to get a better surface cure. One of it, very well known, is inert gas blanketing. This works very well, without any issue. The problem is that it's not available on every kind of machine, and it's quite costly. You could do the same kind of principle by putting on a laminating sheet, protective film if you like, and cure through the protective film, and afterwards you get it off. But you can again imagine that it's a costly way of doing this because you have a lot of waste. And if you could recuperate it, okay, then it's less costly, but otherwise it's also not the best way to go forward. There are some additives that, like waxes, that migrate to the surface. And this migration to the surface then blocks the surface and prevents the oxygen to go really deep into the coating, and then you will get surface cure. The problem is if you add these additives, I don't know about jetting properties, and also you will completely change the surface of your ink, so probably the aspect of your ink will not be the same as well, nor will be the overall properties of your ink. What a lot of people have been doing is simply increasing a lot of the photoinitiator concentration in the ink. That's not only quite costly, because the photoinitiator is generally speaking the most expensive part of your formulation. Also, it does not help a lot. The photoinitiator, if it's designed to help for true cure, you will have true cure. If it's not really designed for surface cure, it will not really help with the surface cure. Then from the side of the LED manufacturers, there has been a war for more power. This has now been stagnated because people start to see the fact that it's not only The peak irradiance switch is important, but also the dose that you really get into your ink. So they are now playing a bit more on dosage. And also the fact that, as my colleague from Exelitas is sitting here, I wanted to mention is that they are working on UV LED with a UVC component, and this UVC component might solve a lot of the problems of the surface cure. In the meanwhile, while this is not commercially available, we believe that we need to work on the chemistry to get this surface cure complete. And I don't know if I need to go through the chemical part of all of this, but generally speaking, the oxygen that is in the coating will form a peroxy radical with the radicals that are already formed. This is very slow propagating, so stopping the reaction at the surface. And if you put in a hydrogen donor, this will interact with this peroxy radical, forming a peroxide and a new radical. And this new radical is again fast propagating, so if you like, you restart your reaction and you push the surface cure to completion. For this chemistry, there are, if you look into literature, 3 different kinds of components that are efficient. These are the thiols, amines, and ethers, and it's in this order. Thiols are more effective than amines. Amines are more efficient than ethers. Thiols have a big problem in the sense that if a UV ink already smells bad, if you put in a lot of thiol, I can assure you that the whole hall will smell of thiols, which is not pleasant if you have to work there for the whole day. Also, it's quite difficult to stabilize a thiol-containing formulation over long periods of time, because you have the interaction with the acrylates. If you want to use ethers, it's a good solution. The problem is that you have to put in a lot. You will change, therefore, a lot of the properties that you get from your ink. Also, if the ink is then supposed to be on a panel, advertisement panel outdoors, the outdoor properties of an ink with a lot of ethers are not great. So, coming to the amines, it's the route that we chose to work on to bring the next generation of a LED booster. So for the project, while working on the project, we came up with 3 different prototypes. They're all, that's what they have in common, they're all polymeric as a Michael addition products, and they have at least 2, or they have 2 acrylate double bonds on the molecule. We wanted to have this acrylic double bonds on the molecule because after curing, we want to be sure that it's built into the network and it's not there as a free moiety able to migrate, or if you like, also cause flexibilization of your ink or what else you could have. Also in terms of labeling, it would not be ideal. We know that it's the amine that is helping the surface cure, so we wanted to put in a lot of amine. So you will see high amine contents for all 3 prototypes, containing all of them the same order of magnitude of acrylic double bonds. And because of the choice of the chemistry, they're all polymeric. So you will have some with a higher viscosity going to the lowest viscosity that we had is the 3rd prototype, 450 millipascal seconds. The color is okay for the latter 2. This one is a bit higher, and this is because of one of the building blocks that we used is already a bit higher in color from the beginning, so you get a polymer that is also a bit higher in color. But it had the advantage that it was of a renewable source, so this is also quite sexy to sell. All right, coming to the application work. This is the pilot line that we have been working on. We have a line with 2 LEDs, a 365 nanometer lamp and a 395 nanometer lamp. They're both 8 watts. One is air-cooled, the other one is water-cooled. The water-cooled one is also an older type. They're mounted on one conveyor, and the distance to the substrate is always 1 centimeter. This is not optimized, but since we do not have the final formulation, as long as we always test in the same conditions, we can compare the results amongst themselves and bring the best product that we could develop to the market. So as said, we applied the coatings and inks with a Michael proofer, 4 microns thickness. on Lanetta charts or plastic substrates. And we did a bit of both. And then afterwards, we investigated immediately after cure the surface cure by thumb twist, fingernail mar, or carbon black. I heard also yesterday that people were talking about the use of FTIR to control the reactivity, to know whether the reactivity is okay. Well, I know from my time in the analytical department that ATR, depending on the crystal that you're using, you're not looking at the surface of your ink. In fact, because the inks are very, very thin layers, you measure the complete bulk. And more likely, if you measure it cured with a UV lamp or with a UV LED, you won't see it. You won't really notice a difference. The easiest way to figure out whether you get complete surface cure is by really doing the thumb twist. The old traditional stuff works the best. Perfect. For the tests, we had to use a starting point formulation, so I used the starting point formulation from Allnex, based on Epicryl 151 as a grinder binder. And in the letdown, we used Epicryl 152. We used a mixture of TPOL and DATX to cure the ink. And then, compared to the reference, we took out 10% of the Epicryl 152 and we put in 10% of the lead booster. And this is the result in reactivity. So compared to the reference, which cured at 1 meter per minute, I'm talking about surface cure. When you add 10% of one of the three different types of three different prototypes, you get an increase, a 15-fold increase of the curing speed. You see that the yellow is always lagging a bit behind. Again, this is because of the competition of the pigment with the photoinitiator. But what is nice and important to mention is that we also had a look at what happened to the viscosity. If you put in this booster, what happens to the viscosity? We did not only look at the viscosity, the working viscosity, but also the stationary viscosity to see if it's not getting hard too much if it's stationary, but that's okay. And what you see here is that, of course, if you put in a molecule with a lower starting viscosity, you also get an ink with a lower viscosity. It's always a bit higher than the reference, although. A nice additional advantage that we saw is that next to this, if you take a look at the optical density becomes better when you add the lead booster. We think that this is because there is a positive interaction, a positive pigment wetting part that is taking place and giving this last slide. And also an increase of the gloss. So if you had a look at the prints, it looked like the colors were more vibrant. As promised, I come to the conclusions. So I hope I've shown you today that these UV PUDs offer really an advantage for new kinds of formulations of inkjet inks. They offer a lot of new opportunities. Of course, this is new technology, so it's not a copy and paste. You will have to rework your formulation know-how. Maybe also your engineering know-how needs to be adapted to the use of this technology. And I think that we already have a quite broad range that is now available on the market for sampling or even commercial to test these different key features. As a second topic, we now have almost at the end of the lead booster project, and we've decided to commercialize the third prototype. So this is now also available for sampling, because we believe that it has the most formulation latitude combined with all the advantages of a lead booster. And then to close off, it's not only an increase of surface cure that we've seen, but also other properties seem to be improved when using this lead booster. This leaves me to thanking you for your attention and a lot of my colleagues that have been working together with me to come to these nice results. Thank you.